First of all, I prepared this part of the whiteboard, and it will be like my reference part of the whiteboard with the major formulas that we need for the exam and in today's exam review session. So I will probably spend like 15 minutes talking about them, and then I will start solving problems related to those to those formulas and ideas. So from the very beginning, we started with what? With basic Coulomb's law, right? We started with Coulomb's law, with introducing electric force, right? And then at some point, of course, we introduced a very, very important idea, the idea of the electric field. And we introduce electric field like you take a small positive probe charge, position at the point where you want to measure the field, measure the force divided by the charge, and that is the electric field. Again, charge, probe charge. Then, if you want to find electric force, just basically solve this formula for F. F equals QE. And again, we've been using it for many times. So at this point, usually students are quite comfortable with that. Then, after we introduce electric field and electric force, which is basically foundation of electricity, we decided to simplify our life, right? And we decided to move from vector quantities to scalar quantities, right? And we introduced, as a result, electric potential energy, U, and electric potential. Electric potential we introduce as the electric potential energy divided by the value of the probe charge. Right? Then we looked, since we introduced the electric potential, right? So we derived formulas for two simple systems. If you have 2-point charges, Q capital and Q small. First of all, again, Coulomb's law I wrote over here, and then corresponding potential energy, right? So this force describes interactions, and then of course potential energy also describes interactions. So that's the expression for the potential energy of a system, 2-point charges. Don't use anywhere else. And then, all right, so using the definition of the electric potential, so you just basically need to remove the probe charge, we introduce the formula for the electric potential created by a point charge Q at the distance R, right? So we're going to use it, and we've used it. Then we also applied all that for a system of a capacitor. So of course, for the in order to introduce potential energy, you need to have two objects. If you have point charge inside of the parallel plate capacitor, then of course potential energy equals to the value of the charge times the value of the electric field inside times the distance from the negatively charged plate, negative electrode, right? It's very important. We need to remember that S is measured from the negative electrode. Sorry. And then we also introduced the expression for the electric potential inside of a parallel plate capacitor. In that case, that is the probe charge. That's the expression for the potential energy divided by the value of the probe charge. And we get expression for the potential inside of a capacitor, E times S. Okay, so then we spent like the whole lecture introducing the electric flux, which is basically a number of electric field lines crossing a certain surface. So for the simplest possible situation, uniform electric field and flat surface, we can use just E dot A. That will be the electric flux. If surface is more complicated and the electric field is not uniform, of course, in that case, you need to use a surface integral, E dot ds, and integrate it over the whole curved surface. So, and that idea of the electric flux is an essential in the Gauss's law, And then we started, we introduced Gauss's law, and then we started playing with that. Gauss's law. Left-hand side, you remember, it's just the electric flux, integral over the closed surface E dot dA, electric flux. And on the right-hand side, it must be equal to the total amount of charge inside of the Gaussian surface. What is the Gaussian surface? Integration is done over any closed surface. Any closed surface can be used as a Gaussian one, right? So here, for the example, I drew 4 charges. Pick a completely arbitrary closed surface. Again, it's basically like a cross section, but 3-dimensional picture, so it's basically closed surface. And so in this case, Q enclosed will be total amount of charge inside of that Gaussian surface, right? So we played with that, and we're going to review today one more time. So then, using Gauss's law, we justified, even sometimes derived, properties of conductors. We applied Gauss's law to find major properties of conductors, pieces of metal. So first, first of all, conductor, the major property, it has tons of free electrons, lots of free electrons, right? And then based on that, we can derive and justify additional properties. So if you disturb a piece of a conductor, what do I mean disturb it? Electrically, you can, dump some amount of charge in the conductor. Or maybe you can expose that conductor to some external electric field. And then you have to wait for a short period of time. Over that period of time, electrons inside of the conductor will be running like really crazy, right? Trying to achieve what? They're trying to make electric field, total net electric field inside of the conductor, zero. Once they manage to achieve it, they stop running, right? They get settled and live happily ever after, right? So, and at that moment, when they stop running and the electric field is zero, we can say that conductor is in the electrostatic equilibrium. So usually, in most of the problems which we analyze, discuss, conductor is and will be in the electrostatic equilibrium. So, in that state, electric field zero, then any excess charge resides on the exterior surface. Then, it's impossible for an excess charge to be inside of the conductor. Then, electric field outside of the conductor, just outside of the surface, is perpendicular. And expression for the electric field outside of the conductor is eta over epsilon naught. Eta, it's a surface charge density. And recently, just what in the previous lecture, we also added additional property. Once we introduced the electric potential, now we also introduce additional property that in the electrostatic equilibrium, the electric potential inside of the conductor is constant, right? And we're going to use it explaining what happens in some simple circuits, like what on Tuesday I'm going to use that. So, properties of conductors. And after that, we moved into describe connections between vector quantities and scalar quantities. Actually, we just compared, we build bridges between the electric field, which is the vector quantity, and the electric potential, right? So it was just recently. We've done it recently. So in order to move from the electric field to the electric potential, we need to calculate. I erased almost. We need to calculate this integral. I already adjusted it for our level, the simplest possible situation. So minus integral of E, x component of the electric field, dx, right? And from between the initial and the final point. And usually in this course, instead of calculating this integral, we just calculate area under the curve. If you plot E sub x versus x, so it's an area between the initial point and the final point, lower limit, upper limit, right? So that's how we can find potential difference between this and that point. And then if you want to move back from the electric potential to the electric field, you just need to, if you have a plot V versus X, it's just the negative slope of that curve at a particular point where you want to know the electric field. Or if you have a function V as a function of X, just differentiate it, put minus in front, and that will be the expression for the electric field. Right? If you also have dependence on y, okay, differentiate with respect to y and add minus. So pretty much that's what we need for the first midterm exam. Right? A few words about vector algebra. Vector algebra, which we reviewed at the very beginning. So what if we have, for example, you know what, let me put number one, problem number one. Right. And so what if we have this situation? What if we have this? Okay, good enough. All right, coordinate system y and x. Right. And let me draw a few vectors. And let's try to find components. Just quickly review certain things. So let's assume that our vector points this way. Right, so let's say it's vector what? A. And let's say we know this angle alpha. Right. So let's say we want to find components. Components, it's very easier, right? So you need to, probably I'll use different color. So that will be the x component, right? And this will be the y component. And so how can we find x component? Since this side is opposite to the given angle, so in order to find this side, it's, okay, let me write e sub x equals to hypotenuse times sine of angle alpha. And since this component points in the positive x direction, it's a positive component. Then y component, since it points down, so this component must be negative, right? So let me write it above. So a sub y will be equal to minus a times cosine alpha. And guys, be comfortable with these functions, sine and cosine. When can you use sine function, and when can you use cosine function? Lots of silly mistakes. Actually, they're not silly, just maybe lack of practice when students use wrong functions, right? So when you need to find adjacent side adjacent to the given angle, cosine function is used. If you want to find opposite side, sine function is used. At least that's how I remember it. Okay, and so this minus we have to put manually because we use convenient angle, not conventional. Conventional angle to find components of the vector is measured from the plus x-axis in the counterclockwise direction, but in this case that's not conventional angle. It's the angle which is convenient for this particular situation. So you have to take care of these minuses and pluses manually. Right. Okay, then another couple of examples more. So let's say we have this, let's say B, and which angle? In this case I decided to give this angle, so let's say angle beta. Okay, so we can find components. In this case, x component is this, y component is that, and both of these components are going to be negative. So let's start with x. A sub x will be, wait, it's a b sub x, not a. B, so it will be absolute value of b, minus in front, right? Because this component points in the negative x direction, and times cosine of angle beta, because again, we're trying to find side which is adjacent to the given angle beta. Then this component, so it will be b sub y. Again, it's a negative because it points, this component points in the negative y direction, downward. So we have to put minus in front, right? So it will be minus b times, and since this side is opposite to the given angle, so we have to use sine function, b sine beta. Okay, I just wanted to remind you about those, if a component is in the negative x or y direction, we have to put minus manually, right? Don't forget that. And usually after our first two recitation classes, usually students remember that. Okay, enough of this. And now, probably the most tedious problem of this exam review, which is similar to problems which we solved in the first two recitation classes. You remember we were adding two vectors. Let's just review that very quickly. Again, I told you that we're not going to introduce something new, something special, something different. We're just reviewing what we had in our recitation classes. Okay, for this problem I will need lots of space, so I'll have to erase this. I will have to erase this. So, let's find net electric field created by 2-point charges. So, let's say the first one is over here. Okay, trying to estimate the amount of space that I might need. So plus, that's Q2 equals to 3 nanocoulombs. Then over here there will be negative charge Q1 minus 6 nanocoulombs, right? And some geometry is given. Distance between these charges. This distance, let me label as A 10 centimeters. Of course, at some point, we will have to convert into meters, so it will be 0.1 meter. And we want to find net electric field, let's say, at this point. And this distance B is, I don't remember, 5 centimeters. And guys, I hope resolution is enough, right? So usually when we had the lockdown, I use Microsoft Teams because that offers better resolution. But running these one-time events, it's easier to use Zoom. But usually Zoom offers slightly less resolution. So we want to find the electric field at this point. Let me label it somehow P, for example, at point P. So we need to find E, all right, at point P. So it's a problem purely about geometry. Okay, so physics is very simple. This charge, point charge, creates its own electric field, right? This charge creates its own electric field, so we just need to add those electric fields as vectors, right? So using principle of superposition. And before we start crunching numbers, let me draw all those electric fields. Contribution to the net electric field from the charge Q2 and from the charge Q1. Okay, so let's start with charge Q2. So it's a positive charge. So the electric field lines, you remember, right, over here, I can draw. If you have positive charge, electric field lines, they start on the positive charge and go to basically infinity, right? So in our case, this point is over here, right? So electric field, as a result, will be pointing that way, right, away from the charge. So that will be the contribution to the net electric field from the charge Q2. So that will be E2. You know what? I started drawing, which is absolutely correct. But usually, I prefer to show one very important thing, without which it will be strange to talk about this problem. We need to show coordinate system because we're dealing with vectors. Vectors without coordinate system, strange, right? So let me introduce coordinate system. Sorry. You can position origin anywhere you want. At this problem, I think the most convenient origin is at the point where we want to find the value of the electric field. So let's say this is Y, and let's say this is X. Okay, now I feel much better. Okay, so now next, contribution to the net electric field from the negative charge, Q1. Okay, so you remember electric field lines over negative charge, because they all are towards the negative charge, right? So our point is somewhere over here, right? So as a result, electric field is going to be that way towards the negative charge, right? So I can draw it here, and this will be this E1. Okay, so, and after that, principle of superposition, we need to add these two vectors as vectors, of course. So it will be E, electric field, which we need to find. Okay, guys, one thing about this problem, which at some point surprised me. I remember once a few years ago, I gave a problem like this on the final exam, hoping it will be kind of straightforward, and some students started feeling not very comfortable because we solve problems like this, finding the net electric force. For example, over here, there was some charge number 3, and we wanted to find the net electric force. And as a result, when they saw a problem like this, some of them actually started panicking what to do, right? In this case, it's just a problem different. This is the problem about finding electric field. And at this point, there is nothing, it's just an empty spot, right? Nothing over there. We just need to find the value of that electrical aura, right? We need to find the net electric field. But if the problem about finding net electric force, net electric force, and there is a charge, then we will have to draw something similar, right? But in that case, those vectors will be vector forces, right? So just two different problems, right? But from the mathematical point of view, the problem about finding net electric field like this, and problem about finding net electric force from the mathematical point of view, they're quite similar, right? But physical meaning, of course, different. That's why I was surprised why students were so shocked by that problem, because mathematically it's basically the same idea. Okay, and you remember the procedure. So first we can find absolute value or magnitude of this force. Field, electric field, magnitude, then find components, then magnitude of this field, electric field, then components, and then we just add corresponding components in order to find components of the net electric field. Okay, so let's start. So first, let me put the first bullet over here, and absolute value of E2, it will be K. Absolute value of the charge Q2 divided by the distance from the second charge, square of the distance from the second charge to the point where we want to find the electric field. So R2, of course, is just B. Yeah, B. Right? So it will be... you know what? I don't want to plug numbers, because you can do it by yourself, right? And you can do that much, much faster than I do that. So B, of course, must be in meters. 5 times 10 to the power of minus 2 meters. Right. And again, you see I put an absolute value because we're trying to find the magnitude. And of course, magnitude cannot be negative. Magnitude of any vector. So if you plug numbers, you're going to get... okay, I will write lower. 1.079 times 10 to the power of 4 newtons per coulomb. Okay, I use significantly more sig figs because it's not the final result. And so after this, we can write components. E2x will be this whole thing, because we have electric field purely in the x direction. And y component will be, of course, 0, because there is no y component. The whole vector is in the x direction. Okay, let me frame with blue. It's not the final result, but important preliminary result. Now let's do the same with the vector E1. So E1. Again, first I want to find magnitude and then components. You remember, it's our second recitation class of this semester. We've solved problems of this type. Of course, charges were different, configuration was slightly different, but idea was exactly the same. So K, absolute value of Q1 divided by R1 squared. So in this case, R1 squared, it's at this distance, right? So let me write it over here, R1, this hypotenuse. So it will be square of A plus square of B. So it will be A squared plus B squared, right? So if you plug again and calculate, and again, you see, I dropped the minus because this charge is negative, because we're trying to find magnitude, and magnitude cannot be negative. Quite often, I see students finding negative values of vectors, which is wrong, of course, right? You need to realize magnitude cannot be negative. Magnitude is just a magnitude. So if you plug numbers, you will end up with 0.431 times 10 to the power of 4 newtons per coulombs. Okay, so now components. Let's find components. In order to find components of this vector E1, we just need to introduce one of the angles, either this angle or that angle. It's up to you. They're both good, right? Which angle I decided to use? I decided to use this angle, theta. Right. Okay. So we can easily find that angle. I prefer to use tangent function. Tangent of this angle, you remember tangent? It's a ratio of opposite side versus adjacent. Opposite side is A, adjacent is B. So we can write, so tangent of theta equals to opposite A, adjacent B, right? And then you can take arctangent. So from here, theta will be equal to 63.43 degrees. Okay, again, I use more sig figs. So, and now we can easily find components. So what will be the x component? Okay, I will probably use red. So that will be the x component, right? And you see, x component points in the negative x direction. So we have to put manually minus in front of our x component, right? Because automatically from mathematics, that minus is not going to appear. So now let's write E1x equals to minus the value of E1 times, okay, it's at this component, so which is adjacent to the chosen angle theta. Adjacent, it means we need to use cosine function, cosine of theta, right? So E1 this, angle that, so you can multiply, and the answer is going to be minus 0.192 times 10 to the power of 4 newtons per coulombs, right? And similar, we can find y component. And y component, it's this, right? Which is in the negative y direction. You see it points downward, negative y direction. So we have to put minus again manually in front of this expression. So minus E1 times sine of theta.
Excuse me?
Yeah.
Why aren't we multiplying by q? Are we using that equation f? Or no, sorry, never mind. We're not using the f equation. Never mind. Wrong. I figured it out.
You thinking about this or something, right? Is that your
Yeah,
question?
I was thinking of the one below it. Never mind. Yeah, I figured it out.
Okay, cool.
Yeah,
I'm still trying to guess what was your confusion. Is it over here why we don't have a second q?
Yeah, but yeah, that was my
Okay,
question.
I figured. And actually, that's why at the very beginning I told you that many students on that final exam were confused because you guys have a very strong habit of calculating Coulomb's force. And we practice that in our recitation classes using that formula, right? KQQ over R squared. And I thought, okay, so I can give basically mathematically, it's exactly the same. I can give you a problem of this type where you just need to again draw electric fields and then add them as vectors. So mathematically, problems identical. But again, as I said, students develop this strong habit of playing with these two charges, multiplying them, right? But this is a different problem. We're just interested in the electric field, not the electric force. Right? Mathematically, they're very similar, but physically, electric force and electric field are two different things. I wouldn't be able to say apples and oranges because from electric field you can get, electric force, you can easily get electric field. But still, they are two different quantities, right? So be careful and see what is in the question. In this case, we need to find electric field. And the expression for the electric field, actually, I didn't write over here. I should have, yeah, it's a missing part. I could write over here electric field of a point charge. Okay, KQ over R squared. I should have added that somehow. Right. Okay. But anyway, so it's good that you cleared it.
Yes.
And that's
thank
why
you.
after that exam, I actually started solving problems of this time, bugging actually, and telling students, guys, be careful, right? Because you're not the first one, you're not the only one, and probably you're not the last one who is confused about this. Just we're trying to find different things. electric field, not electric force. And for your problem, okay, which you thought of, in that case, we would have to have a charge number 3 over here, but here we don't have any charge. Right? It's just an empty spot. We just want to find the electric field. Okay, so y component. Now I just need a number for the y component. Minus 0.385 times 10 to the power of 4 newtons per coulombs. And probably my neighbors also are confused. I got a new neighbors a few days ago. The previous one went through lockdown with me, so they're familiar with my lectures. But these guys are new. So, all right. So these are components of the first first vector. So now we just need to add them, right? So in order to find the components of this electric field, net electric field. So that was the first bullet, second bullet, and now the last bullet. So E, it's this E. It's we need to add E1 plus E2. Of course, right now it's written in a vector form. We need to add, of course, components, right? Corresponding components, X component and Y components. We just need to add. So EX will be E1X plus E2X. Here and there. So positive, negative, I'm not going to subtract. I will just use my notes, right? So it will be positive 0.887 times 10 to the power of 4 newtons per coulombs. And similar for the y component. EY equals to E1y plus E2y equals, in this case it's easy because this component is 0. And every time I usually try to arrange it in such a way so that y component, one of the components is 0, less calculations. All right, so it will be this over here. So it will be minus 0.385 times 10 to the power of 4 newtons per coulombs. Okay, so components X and Y of the net electric field. And of course, now it's worth of framing in red, because after this point you can say, I found components. I know almost everything about this vector E, right? But usually book and mastering physics and on the exam, we usually push for slightly more. Find a magnitude of this vector, net vector, and then direction. So let's do the same. It's basically very, very similar steps to the steps which we used in the recitation class, the second one. So now magnitude of E. Magnitude of this net electric field. This one, right? So EX squared plus EY squared and square root. So I can write that E equals to square root of EX squared plus E sub Y squared. Right. Again, in the recitation class, we spent more time drawing additional pictures, right, in order to explain. But at this point, I hope you are familiar with all the steps, right? Just reviewing. But if you need more explanations, just tell me, right? Don't feel, I know, awkward asking. So if you plug, square this plus square that and take square root, you will end up with 0.967 times 10 to the power of 4. Again, units, newtons per coulombs. At this level, we use newtons per coulombs, and then when we introduce electric potential, we started using volts per meters. Newtons per coulombs and volts per meter is basically the same thing. You can easily convert them. And so now the final, so direction of this electric field E, and usually direction relative to the x-axis most of the time, right? Let's use this angle phi to describe a direction of this vector E. So we just found the magnitude and now direction. So in order to find direction, this angle phi. You know what, probably let me redraw the picture, additional picture, because at this point, some students are still confused. What are we doing? But if I add additional pictures, usually everything becomes clear. So let me draw this electric field over here. So that's in the fourth quarter. So that's our E. And what we just found, we found X component. So that's our EX. And we found Y component, EY. And angle which we want to find, it's this angle phi. So now pretty much we just need to look at this right triangle, this point, and that point. So it's a tangent of that angle. It's a ratio of opposite side, which is the Y component, just the length, absolute value, and divided by the absolute value of the X component, just property of a right triangle. Because at some point on this point, this picture becomes too busy, and additional picture usually helps. Right? Although we're talking about very, very simple things of vector algebra. So tangent of this angle phi, tangent phi equals to, again, you see absolute value, because now I just want to know the length of that side, this side, versus length of that side. So it's E sub y divided by E sub x. Okay, my handwriting is getting worse because here I have flat surface and it's difficult to write. So of course you can invert it in order to get phi, and after the inversion you will get 23 degrees and more sig figs. Wait, 2346. Okay, let me fix it. 2346 degrees. So again, the major goal of the problems like this at the very beginning of the semester, we just wanted to review how to work with vectors, right? Because physics here not much. Okay, this charge creates electric field, this charge creates electric field, two vectors, add them up, and that's it, right? Okay, so now let me add additional very short part to this problem. I can say this is, I don't know, part A, and this will be second part B. So let me call it A, and this part B. Then you remember closer to what a couple of weeks ago we introduced the electric potential, right? So electric potential, and so now we can also describe that point, electrical aura at that point, using electric potential. So over here we described it using electric field vector quantity, but now we can also describe it using the electric potential. And you remember electric field and electric potential, they describe exactly the same thing, that electrical aura. So let's find electric potential at point P. So now let's find V at that point P. And this finding electric potential is really, really simple. You see how much time we spent here, and now see how much time we will spend finding electric potential. So V at P, subscript P I decided to use. It will be contribution from this V1, contribution from the charge Q1, and of course that's V sub 1, and plus contribution from the second charge, V sub 2. And the expression for the electric potential created by a point charge is over here. K, the value of the charge, divided by the distance from the charge to the point where you want to find the electric potential. So now we just need to apply that formula twice. So it will be K. This charge is negative, right? Okay, first let me write Q1 over R1 and plus K, Q2 over R2, right? R1, again, it's still the same. It actually equals to B, and wait, that's R2. That's R2, sorry. In R1, it's a distance from this charge to the point P, of course, right? So, which way I wrote it? So it will be 8.99 times 10 to the power of 9. It's okay. All right. Okay, I can write units. And then I can factor out k, right? And then what will be inside of these brackets? K1 minus 6 nanocoulombs minus 6 times 10 to the power of 9 coulombs. Again, another typical mistakes in the problems like this, don't forget about nanocoulombs. On the exam, if you forgot about the meaning of micro or nano or pico, whatever prefixes are used, just raise your hand. We will come and tell you, right, if what you think is correct or not, right? We don't force you to remember all those prefixes, although it's good to remember them. Right? At some point, you will remember, right? If you're going to work in some kind of research or engineering, right? But at this point, you're still learning. So don't forget minus 9, 10 to the power of minus 9 coulombs, right? And R1 is just B. Hold it. It's yeah, it's good. It's Q1. Yep. And divided by now it's a first power of R. Over here we had R squared, right? Over there, here R squared, but now it's a first power of R. Again, don't make, sometimes I see students making those really unnecessary mistakes, right? And again, all those formulas are given in the formula sheet, you just need to find them. Right? So R1, it's a square root of a squared plus b squared, right? The value of that hypotenuse. And then Q2, it's a 3 nanocoulombs, 3 times 10 to the power of minus 9 coulombs, divided by, now it's a value of B, of course, in meters. Right, of course, let me emphasize that that must be in meters. Right, and that also must be in meters. Okay, the only thing, since I was just decided to add this part almost at the last moment before the exam review session, so I didn't calculate the number. But you can do it easily on the exam if you see something like this, right? You can crunch numbers. So pretty much why I decided to add this, again, to demonstrate how much easier to work with scalar function relative to the vector function. And that was the goal, that was motivation to introduce those potential energies and the electric potential to simplify lives in terms of calculations. Right? And significant improvement. Okay, so that's the second, and as I said, probably the most tedious problem usually in the semester, in the whole semester. So the next problem, as you asked me, where is the second charge? The second problem is about finding the net electric force. There are 3 charges, right? 1, 2, and here there is a third one, and you need to find the net electric force. In that case, of course, you will have to use this formula: K Q1 Q2 divided by R squared. But here, since we find electric field, there's only 1 charge all the time, right? In order to find expression for the electric field created by a certain charge. This problem I'm not going to discuss because mathematically exactly the same. Right, so you can look by yourself practicing for the exam. I'm not going to solve because really similar situation. So now, if you have any questions or comments, go ahead, and otherwise I will just look at a couple of conceptual questions, simple conceptual questions similar to the one which you had in lectures among clicker questions. And then we will start discussing Gauss's law. Can I start erasing? Number 3, conceptual. CQ, conceptual questions. We need to find electric field and the electric potential of two charges. So let's assume that we have a square. I'm looking, do I have any squares around me to draw them faster? So let's assume that we have a square. Right. Okay, and maybe let me show that this is a square. And two charges. The positive one over here plus Q, and the negative one at this corner minus Q. The same in absolute value, plus Q minus Q. And we're interested in the information about the electric field and the electric potential at the center of this square. So we need to find information about E and V at the center, of the square. Again, I put a dot, but it doesn't mean at the center there is any point charge. No, it's nothing. It's an empty spot, empty space, right? So we have only this charge, positive charge, this negative charge. And of course, they both create sort of like a net electrical aura around themselves. And of course, we can find net electric field and net electric potential at any point we want. So we're interested in this point, right? So let's start with the electric field. And so electric field, contribution from the positive charge. You remember, electric field lines start on the positive charge and go to infinity. So pretty much I can draw something like this, like that, like this, like that. But I'm interested in only at this point. So the contribution will be this. So it will be E1, right? Then negative charge, electric field lines toward, right? So through this point, there will be electric field line going towards the charge. So I can draw this electric field. And of course, in absolute value, this electric field and that electric field are going to be equal because charges are the same. Distance from the charge to the point in question, from the charge to the point in question, distances are the same. So the electric field, KQ over R, magnitudes of the electric field are going to be exactly the same. So this and this are the same. So it means that if we add them up, the net electric field will be pure horizontal, right? So electric field will be pure horizontal. So that will be the direction of the net electric field. So I can write, so E is horizontal. Okay, and to the right. Then if you are interested in the net electric potential, KQ over R. And of course, we need to apply that twice, like what we did over here, basically, right? But now it's conceptually V equals to what? KQ, it's this one, over R, it's R, and that distance is R, Q over R. And this will be negative plus K minus Q over R. So contribution to the net electric potential from this charge is positive, from that charge is negative, and they're exactly the same in absolute value. So this plus that is 0. Right. And you remember we had a question, like a couple of questions like this in a couple of lectures. Right. And I told you that sometimes I give questions like this among multiple choice questions on the exam. Okay, so you see, it's not that complicated at all. So there's a second example. You can read it by yourself because it's very, very similar. Okay, so now let's review Gauss's law. And then we will talk about the electric flux. I prepared a couple of, maybe 3 conceptual questions But first, Gauss's law. So we just practiced finding the electric force, electric field, and electric potential of point charges. And now let's practice Gauss's law. Right, then there will be a problem about charges moving inside of the capacitor, but that will be closer to the end of the exam review session. So now Gauss's law. And I prepared this problem. Spherical, non-conducting sphere with a concentric hole. Okay, let me draw that. Maybe I will draw it here. So this is a sphere with radius. Okay, let me draw also a hole, and then I will label. No. Okay, it's better. So, material, non-conducting material, it's here. And guys, when you see problems like this, read problem carefully. If it says metal, then of course you can use properties of conductors. But if the problem says it's a non-conducting material, don't use this. Because I see in the past, I would never say quite often, but some students confuses that, and they use properties of conductors describing a non-conducting material, which is not good, right? So in this case, let me write, it's a non-conducting material, non-conducting material. And I will emphasize. So read problem, right? And don't make those unnecessary mistakes, right? Because again, every semester I see some students make those mistakes. Okay, so that's not the whole story. So now radii, let's say this radius A, this radius B, as far as I remember, yeah. And now let's position at the center of this structure over here, positive charge Q. To have slightly more complicated problem. Okay, so let me position here plus Q. Right? And then what else is given? The total, this sphere, not sphere, spherical shell. This spherical shell is charged with the total charge Q, and that charge Q is uniformly distributed over that shell. Okay, I can actually draw a few pluses. Right, and non-conducting material. Right, so let me write. So what is given? Q. It's a charge uniformly distributed over that shell. Then radii A and B are given, and charge at the center Q small. So that's what is given. And we need to find, actually the question can be about finding electric field anywhere. For example, finding electric field outside, electric field inside, electric field over here, right? But to practice, I picked the most complicated part of the problem, finding electric field in this spherical shell, basically between radius A and radius B. So I just picked the most complicated part because procedures are very similar. So let me write, so find E for R between larger or equal than A and smaller and equal than B. So pretty much we're interested in the electric field in the spherical shell, right, inside of that non-conducting material. Okay, and for the problems like this, you remember the most convenient law to apply it's a Gauss's law, because we have nice spherical symmetry, spherical symmetry, nice distribution of charges, and application of the Gauss's law is basically a piece of cake, I would say, right? But of course, after practicing many times, of course, it's a piece of cake. But for you, of course, it might be slightly challenging. So Gauss's law, let me rewrite it over here. E dot dA and Q enclosed over epsilon naught. And as usual, you remember which step do you have to make? The first one, you need to pick a Gaussian surface. Any Gaussian surface can work, right? You remember, it's a universal law, no restrictions. You can pick any closed surface and you can apply Gauss's law. But in this case, in order to solve the problem, in order to get what we want to get, we need to pick the best surface, the most convenient, which will allow us to use the symmetry of the problem. And of course, you understand that I'm talking about the sphere, concentric sphere. And of course, that sphere must be in the region where we want to find electric field. So let's pick a Gaussian surface. It will be over here, and I will use dash line, right, of some arbitrary radius r. Right, and of course, Gaussian surface must be in the region in which you're interested in. So once we pick the Gaussian surface, actually I can write that this is our Gaussian surface. Right. So now we can start evaluating this integral and start calculating Q enclosed. So usually I start with integral. So let me just rewrite it. And again, you see I'm repeating the procedure which we discussed in the lecture. Just this configuration is slightly different relative to what we discussed in lectures. So first step, usually I suggest let's draw all of these vectors, electric field and the area vector, on our Gaussian surface. Because again, we integrate over the Gaussian surface. So electric field, I'm not going to justify the direction. I justified it in the lecture, right? And we showed that electric field is radial. Okay, I can, you know what, let me start with the area vector. Let me take a small patch, for example, over here, right? And then I will continue drawing electric field. It's better to start with the area vector dA. So area vector, you remember, by convention, it must be perpendicular to the surface. And for the Gauss's law, it must point towards the outside. Right? So it means that since we pick this sphere, so area vector must be radial, dA. Or I can take it, for example, here, I know, some patch. So this will be dA, or over here, it doesn't matter, so that's dA. And then electric field, from which I started. Again, I justified in the lecture that electric field is going to be radial because of the spherical symmetry. Right, so I drew already electric field over here. Then I can draw it, for example, over there, or here, E. And you see at every point on the Gaussian surface, these two vectors, E and dA, are parallel to each other. As a result, we can simplify this expression and we can get rid of a dot product, get rid of vectors. So E is parallel to dA, right? And the dot product will be E dot dA equals to E dA. Just applying definition of a scalar product, dot product, times cosine of angle between these two vectors. And since these two vectors parallel to each other, so 0 degrees. Right. And so I can write it. So since this is equals to 1, so it will be E dA. Okay, let me extend these brackets, explanation box. And so now I can write integral over the closed surface, our Gaussian surface, E dA. Again, what's the major difference? Here we had vectors. Now we had just the products of components. Components, products of their magnitudes. magnitude of E, and absolute value of dA. So now we don't have vectors. And so the last step, because of the symmetry of the problem, right? So it doesn't matter where you sit at this point, or this point, or this point on the Gaussian surface, electric field strength is going to be exactly the same, exactly the same. So I can write, so E, okay, since E equals to constant on the Gaussian surface. So any constant can be taken outside of the sign of integration. So we can extract the electric field from the sign of integration. So it will be E integral of dA. And at this point, again, from the mathematical point of view, still plenty of integration must be done to find the value of this integral. But we know the answer. It's just the area of that sphere with radius r small. So it will be pi r small squared, r small squared. So that is equal to 4 pi r squared. And again, guys, at this point, when students need to find areas over some circle or volume of the sphere or these simple formulas or circumference, right? I know maybe like 10-15% of students making just silly mistakes using the wrong formula, right? And those formulas, I think they're given in the formula sheet, right? Just don't rush. Look if you're actually using the correct one, because it's really silly, right? To see when instead of area students use the volume, for example, or instead of area they use, I don't know, circumference of a circle. I've seen different things, right? So that's why I'm warning you, don't make those really unnecessary mistakes. So now let me rewrite. So E times 4 pi r squared equals to, and according to the Gauss's law, this is the value of the flux. It must be equal to Q enclosed divided by epsilon naught. Q enclosed divided by epsilon naught. And now we need to find Q enclosed. And that's where tons of mistakes. Usually, maybe like 30% of students usually write the correct expression for the Q enclosed. And for me, it's all the time difficult to understand why, and that's why this semester I gave you that quiz number 3 with lots of questions about finding charge density, linear charge density, surface volume, finding charge here, charge there, right? So I decided to to push you harder in that, because it's barely physics. You just need to look at the picture and see which charge you need to find, and then divide or multiply, charge with the volume, or charge density and the volume. Okay, so Q enclosed. So first of all, let's see which charges we need to count. Again, all the charges physically embraced by our Gaussian surface. Our Gaussian surface is this. So pretty much we just need to find all the charges inside of that sphere with radius r. Immediately you see this charge plus q, it is inside, physically inside. So it must be there. And then, of course, we need to find also this charge, which is between the sphere with radius r and this sphere with radius a, because inside of this hole there is nothing. Okay, and this charge we will count separately. So we need to find, okay, let me use this highlighting. So that's where also Q enclosed, right? So here and that charge plus Q. So that's the amount of charge, Q in. Right. Okay, so now let me write Q in equals Q small, because it's fully inside, stays at the center, so we need to count it. And now we need to find this. Which way I label it? Okay. Let's assume, for now, of course, volume charge density right now is not given, but we will find in a second. So for now, let's assume that volume charge density we know. So what do we have to do with the volume charge density in order to find the amount of charge in this thinner shell highlighted? We just need to multiply this density by the volume of this thinner shell. Volume of that shell, it's the volume of the sphere with radius r small, this greenish area, and minus volume of the sphere with radius a, because inside of this sphere with radius a, it's empty. It's empty. And again, this charge q is we already included, right? So we just need to multiply it by volume of the sphere with radius r small minus volume of the sphere with radius a. You see, we subtracted the whole volume of the whole. Inside of sphere with radius a, there is nothing, right? Okay, and of course we can easily find this. It's a 4 pi r squared minus 4 pi over 3 r to the power of 3, 4 pi over 3 a to the power of 3. So now how can we find this volume charge density? Okay, let me rewrite it. Q plus and volume charge density. Again, we discussed it, and again, you practice in your quiz. We can find this volume charge density using the total charge Q capital, which is uniformly distributed over this shell. Right? So we just need to take total charge Q and divide it by the volume over which that charge is distributed. So Q and divided by this volume of this shell, right? So it's a volume of the sphere with radius b, right? Minus volume of the sphere with radius a, because charge Q capital is distributed between these, right? Between these two spheres. So it will be volume with radius b, the outer one, and again minus the whole volume of the sphere with radius a. Okay, my cables are getting loose. Cables for the mic. Okay, so that's our rho, and multiply by that. Volume with the sphere of radius r small minus volume of the sphere with radius a. You see, here we're subtracting the whole volume of the sphere with volume of the whole, and minus again subtracting volume of the whole. Okay, so now we just need to write explicitly. So it will be Q plus Q capital divided by 4 pi over 3 b to the power of 3 minus a to the power of 3. So that's our volume charge density. I just wrote explicitly. And multiply by this 4 pi over 3 and r to the power of 3 minus a to the power of 3. Another mistake which I see from time to time, not often, but maybe a few % of students make this mistake. Sometimes the students write, instead of subtracting cube of this and cube of that, r to the power of 3 minus a to the power of 3, they write something like this, r minus a to the power of 3. Right? Which is, of course, wrong. We're subtracting volume, so we cannot subtract radii and cube that. It's completely two different things, apples and oranges, right? Okay, so 4 pi over 3 can be cancelled. 4 pi over 3 can be cancelled. Right? So as a result, we have the answer for the charge Q small plus Q capital in the ratio r to the power of 3 minus a to the power of 3 divided by b to the power of 3 minus a to the power of 3.
Excuse me?
Yeah.
Can you just go over one more time how you got the Q inside up top, like that first equation, Q plus P VR minus V?
This one, right?
Yes, please.
Mm-hmm. Okay, Q enclosed, this Q enclosed, by definition, it counts all the charges physically present inside of the Gaussian surface. All charges physically present. So this is our Gaussian surface, right? And this charge Q small, is it inside of that Gaussian surface or not?
Yes, it is.
Of course inside. That's why I added this Q.
Yeah.
And then I'm adding this amount, the charge which is distributed over that thin shell.
Oh, okay.
So if we had, for example, over here another charge, I would add here, I don't know, Q2. If I had maybe another charge, okay, I will keep adding since all those charges are inside of the hole. We just need to count all charges physically present inside of the Gaussian sphere. And Gauss's law doesn't care where those charges are. As long as they are inside, we need to count them in. For example, I can grab this charge Q2 and move it over here. It's still inside, add it. Right? I'm just looking at the picture and counting all the charges physically inside of the Gaussian surface. Make sense?
Yes, thank you.
Very simple idea. Look and count if the charge is inside. That's the Q enclosed. And in the lectures, when we discussed Gauss's law, I discussed very similar problem. Actually, I didn't discuss it in the lecture, but I added to my notes without this charge Q small inside. So pretty much in that problem, just this is missing, and I will just discuss about this charge, and then of course that's Q enclosed for that particular problem. But for this problem, just add Q small. It doesn't add significant to complexity. Right. So now we found Q in, and now we just need to plug it. All this thing. We just need to plug into our Gauss's law and finish the problem. So we will have to just move this 4 pi r squared to that side downstairs and solve it for E. And you know what? Since I'm running out of whiteboard, I will just show that this goes over here. So I will just rewrite this line over there. So E times 4 pi r squared equals to Q enclosed divided by epsilon naught. So all this thing divided by epsilon naught. Oh, and conservation of brackets. One more bracket I needed to add. So I rewrote this with explicit expression for Q enclosed. So now we just need to solve it for E. So this pretty much goes to the denominator. So E as a function of R equals to, so it will be 1 over 4 pi epsilon naught R squared. And that expression, so Q small plus Q capital R to the power of 3 minus A to the power of 3 and divided by B to the power of 3 minus A to the power of 3. So that's the answer. So this part, calculating the electric flux, is very similar to what we, not very similar, exactly the same like what we did in the lecture up to this point. And then just the procedure of finding Q enclosed is slightly different. Any questions about Gauss's law? Now the next conceptual questions, couple of conceptual questions related to the Gauss's law. So, problem 5, and which will consist of a few parts. You know what? Let me start with this one more complicated. I decided to give this problem during the virtual classes. Let's assume that we have this situation: cylindrical surface. Cylindrical surface. Let me draw it here. Right. Right. Size doesn't matter. And there are 3 charges. I decided to add 3 charges. Some of them positive, some of them negative. All right, so let's say this is plus 5 coulombs, and this is minus 5 coulombs. And then one charge is over here, plus 2 coulombs. So these 2 charges are inside, and that charge is outside of this cylinder. And some additional information is given. Of course, so there is an electric field. Since all these charges are going to create their own electric field, so there will be, of course, net electric field. And of course, we can talk about the electric flux. Okay, so some information about the electric flux is given. So let's say the flux, electric flux through the top, equals to minus 15 newtons per coulombs times meters to the power of 2. Right? Then there is also flux, the value of the flux through this cylindrical wall. So flux through the cylindrical wall equals to 10 newtons over coulombs times meters squared. So knowing this, we should be able to find flux through the bottom. So what we need to find? Flux through the bottom. So the whole cylinder consists of 3 parts: top, bottom, and the cylindrical wall. We know the value of the flux, through the top. We know the value of the flux through the cylindrical wall. We want to find the flux through the bottom. Right. Okay, let me erase this. And now it can sound complicated, but actually it's not that bad. Let me ask you first question. Can you tell me what will be the total flux through the whole this cylindrical wall? So first, let me ask, so what's the total flux? And at this point, you should be able to, not guessing, you should be able to give answer with a justification. Gauss's law. Look at the Gauss's law. You see?
Would it be negative 10?
Easier. Look, what do we have in the Gauss's law? The left-hand side is just the electric flux, total electric flux through the closed surface. In our case, the closed surface is this cylindrical cylinder. So total flux equals to what? Q enclosed over epsilon naught. What's the total amount of Q enclosed charge inside of the cylindrical wall? Plus Q minus Q. Q enclosed is 0. Q enclosed is 0. So it means that the total flux through our cylinder is 0. We know the value of the total flux using Gauss's law immediately. You see that? That's the beginning and probably the most crucial step. Okay, so let me write. So Gauss's law, using Gauss's law. So electric flux equals, okay, that integral of E dot dA equals to Q enclosed over epsilon naught. So that's what we are connecting. I asked, okay, about the total flux, and it is equal to Q enclosed over epsilon naught. This charge plus 2Q is outside. We don't care. Gauss's law doesn't care about the charge. We only care about the charges inside, plus Q and minus Q. Okay, so it will be plus 5 coulombs minus 5 coulombs divided by epsilon naught. So that is 0. So the total flux is 0. So phi total is 0. See that, guys? If net charge inside of the sphere, not sphere, a closed surface is 0, the total flux to that closed surface is 0. So now we know the total flux, and we also know the flux through the top and the wall. So let me write, so the total flux, of course, will consist of flux through the top plus flux through the bottom plus flux through the wall. Flux is an integral. So total flux through this complicated surface can be divided into 3 flux. And we just found this. It's 0. This value is given, minus 15. This value is also given, 10. And that is basically what we need to find. You see? Once you realize what's the value of the total flux, the rest is just a question of subtracting 2 or 3 numbers. So let's solve it for phi at the bottom. Phi bottom equals to this, and this goes to that side with minus. So it will be minus flux through the top minus flux through the wall equals to, right? So flux through the top minus 15. So it will be, okay, let me write underneath minus 15. Okay, I'm not writing the units. Too much to write. Right. So this is minus 15 and minus from the formula, right? Because I moved this side, this term to that side, minus, and then minus because the value of the flux. And then minus the flux through the wall, cylindrical wall, 10. So plus 10. 15 minus 10. Yeah, positive 15 minus 10. So the total flux is going to be, the flux through the bottom will be plus 5 newtons per coulombs times meters to the power of 2. Okay, let me check if I got the same number. Yeah, the same answer. You see, once it is explained, it's not that bad. But I remember, some students, significant number of students made mistake in this question. Right. But again, remember, in the Gauss's law, the left-hand side, it's the flux, total flux through the Gaussian surface. Right. In this case, we can treat that as our Gaussian surface. And since the total charge inside is 0 plus 5 minus 5, so the total flux is 0. And we also know the total flux through the surface consists of 3 parts, top, bottom, wall. Make sense? Okay, since you're quiet, I assume that yes. Maybe one additional question about the flux, total flux. So let's say part 5, let's say this is question A, then let's say at question B. So let's assume that we have, again, some cylinder, closed surface. And let's say we have some charge over here outside, which is, let's say, plus Q. And the question is, what's the flux through this surface? electric flux through that cylinder? And the answer is like that. It should be immediate. Think about Gauss's law. Again, closed surface, we can legitimately apply Gauss's law. And so according to the Gauss's law, again, the left hand side is the flux, pretty much that's the question. And it is equal to Q enclosed. Look inside of the Gaussian surface, which we pick, that there is no charges. This charge is outside, we don't care. Gauss's law doesn't care, not we. We might care, but the Gauss's law doesn't care about charges outside. Since inside there are no any charges, Q enclosed equals 0, so the flux will be 0. Right. Q phi E equals to Q enclosed over epsilon naught. Q enclosed is 0, so the total flux is 0. Right. Or another question similar to this I prepared, let's say part C. Again, let's assume that we have a cylinder. And let's increase number of charges. So let's assume that we have here a charge, I know, plus Q. Then inside there is a over here plus Q, over there minus Q. Again, the same question, what's the flux? Since it's a closed surface, again, we can use Gauss's law, and I can ask the question, what's the total flux through this closed surface, which is a cylinder, right? So I can write, so what's the flux? And again, Gauss's law. According to the Gauss's law, again, let me write Gauss's law. So flux equals to Q enclosed over epsilon naught. This charge is not enclosed, forget about that. This charge is enclosed, this charge is also enclosed, and if you add them up, of course you will end up with 0 plus Q minus Q, 0. Right? So it will be plus Q minus Q divided by epsilon naught. So flux through that cylinder will be 0 again. And that's what I used basically. Here we have plus Q minus Q. Here I gave you plus 5 coulombs minus 5 coulombs. But idea is the same. Again, since in these problems, questions are about finding electric flux, it's kind of simple, very fast. But in the previous problem where we apply Gauss's law, the question was about finding electric field. And of course, those problems are significantly more complicated because you need to extract that electric field from the sign of that integral. But if the question's about finding just electric flux, it's much, much faster. Enough of Gauss's law. Now, properties of conductors. Let's just say a few words about properties of conductors. I prepared a couple of problems. They're more like conceptual. Okay, let me start with this question, and then I will talk about that one. So we have a, I created this conductor, drew of this shape. First some kind of rectangle. Okay, not a rectangle, with round corners. And let's assume that this conductor is charged. And let me write that Q total. Okay, I need step slightly more. So let's say Q total equals to minus 6 coulombs. So again, let me write that this is metal conductor. I use metal because less symbols to write. So we have a conductor, and Q total equals to minus 6 coulombs. Then there are two holes, two voids inside of this conductor. And again, those voids don't have connections to the outside world. So let me draw the first one over here. Just for fun, I just created complicated holes with a complicated shape. First triangular, and then circular, right? And the, again, metal is here. And now let me dump a few charges inside of these holes. So over here will be -2 coulombs. Then here let me add -3 coulombs and one positive charge to balance, +8 coulombs. So, and you know the question, right? You can guess the questions. We need to find the total amount of charge on this inner surface, okay, interior surface. Then amount of charge on that interior surface and the amount of charge on the exterior surface, right? You remember we discussed problems like this in our recitation classes and in lectures. So let me write what needs to be found. Find QI1. I stands for interior, right? First interior surface. Then QI2. And of course, Q out, charge on the outer surface. So let's start with interior surfaces, QI1. And you should be able to answer these questions immediately without basically, okay, it's a bad thing to say without thinking, right? But since we've answered similar questions many times, right? So what happens? Again, we assume that this metal is in the electrostatic equilibrium. So electrons stop running, right? Electric field inside 0, right? And so what happens? Electrons inside of this conductor sees this negative charge. And of course, they're going to run away, leaving behind positive charges around this interior surface. Again, the electrons run away in order to what? In order to make electric field inside of the conductor 0. Or in simple words, we can say electrons see that negative charge, and you remember, like charges repel, of course, they're going to run away, leaving on this surface positive charges. And with exactly the total amount of charge on that interior surface will be equal to the absolute value of the charge inside, but of course with the opposite sign. So over here we're going to have plus, 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 right? Of course, distribution is going to be complicated because it's not a cylindrical surface, it's a triangular surface, right? But we don't care how the charge is going to be distributed. We know that the total amount of this positive charge will be +2 coulombs. If you want to prove it, you have to use Gauss's law like we did in the lecture. Pick a Gaussian surface just below the surface and apply Gauss's law. So we can write immediately, so Q in on the first surface, inner surface, it will be +2 coulombs. And let me show it's here. So the same in absolute value, but opposite with sign. Then here we have battle of two things. Of course, electrons see this positive charge. They will try to run towards this surface, but they see this negative charge. Of course, some of them will change their mind and they're not going to run this way. So pretty much in this case, we have to balance two things, or we can just simply add this charge with that one. So the net charge inside will be +5 coulombs. So it means that on the inner surface number 2, there will be -5 coulomb charge. So just find the net charge inside. So, and the charge with the opposite sign will be on the inner surface. So over here, so I said it will be +5 coulombs, 5 coulombs inside. So on the outer surface, there will be negative charge. So it will be minus, 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 minus. And let me show it's over here. So that Q I2 will be equal to a minus 5 coulombs. 8 minus 3, 5. Total charge inside, and of course on the surface, going to be minus 5 coulombs. So this and this usually answered like that. And now we need to find the amount of charge on the outer surface right over here. Because again, you remember, in the electrostatic equilibrium, excess charge cannot be inside of the conductor. It can be only on surfaces. Outer surface, and if there are inner surfaces, then also sometimes on the inner surface, if there are charges in the holes. Right. So in order to find the charge on the outer surface, we just need to apply conservation of charge. Conservation of charge inside of the conducting material. Okay, let me write that down. So now we need to apply conservation of charge. Conservation of charge in the conducting material. Why I'm writing this conducting material? Just to emphasize that this charge minus 2, this charge plus 8, and that charge minus 3, they are not part of this conducting material. They are inside of those holes, inside of the vacuum, so they are not part of the conductor. So I'm just trying to count all the charges inside of this metal. Right? And you remember, again, as I said, charges can be either on the outer surface or inner surfaces, right? You remember I gave you this analogy. It's sort of like a, if you have 2 rooms and you know that there are total number of people 10, if there are 7 people in one room, 3 people must be in the second room. The same story here. If we know the total charge is this, then some of those people will be on the inner surface, some of those will be on this inner surface, and some will be on the outer surface. So we just need to add all those charges on all those surfaces up. So let me write, so Q total equals to QI1 plus QI2 and plus Q on the outer surfaces. On outer surface. Just adding all these charges up. And so we know Q total, we found this charge and that charge, so we just need to solve it for Q out, right? So you remember we've done it in our lectures. In the recitation classes, so I can write, so Q out surface equals to Q total minus QI1 minus QI2 equals. So there's just a question of adding numbers. Total minus 6, then minus Q inner 1, 2 coulombs, this charge. And I2, it's a minus 5 coulombs. So let's see what we're going to get. Minus 8 plus 5 minus 3 coulombs. I'm getting, right? Yeah. So minus 3 coulombs. So that's the amount of charge on the outer surface. You see, it's quite simple. And most of the time I give a problem like this among multiple choice questions. So I can add here part A, and now let me quickly add part B. Okay, any questions on this? Okay, so now next one. Again, it's very similar to the clicker question from the lecture. Let's assume that we have metal sphere. And let's say we have 2 charges, I know, Q2, and here let's say Q1. And the question is, what's the net electric field at the center of the sphere? And the answer again is, it should be like this immediately, right? Again, we assume that we wait for a short period of time so that our conductor reaches electrostatic equilibrium. And in that case, electrons will distribute themselves properly around the surface, right? Making electric field inside of the conductor 0. Right? So it doesn't matter how complicated distribution of charges outside of the sphere is going to be, right? Maybe I can add another charge here, another charge there, but electrons, like brave soldiers, they will take care of that effect, take care of they distribute themselves in such a way so that the net electric field inside of the conductor will be anyway zero. Right? So E equals 0. Right? And it's not just at the center, it will be at every point inside of the conductor. Electric field will be 0. Right? Just wanted to, again, remind you. Okay, now, enough of this. Now it's time to solve problems about some charges moving in the electric field or electric potential, and basically we need to practice how to solve problems using energy approach, right? Which we solved like what, a few recitation classes ago. Two-point charges. First, let's say, okay, let me draw and then I will explain. So let's say we have identical charges, Q and here, let's say Q. They can be both positive, both negative, it doesn't change the situation, right? So first, initial situation, we hold both of these charges, so they don't move. Initial situation, right? So let's say this is I initial, and this distance between charges is D. Then we will release this one. So we still hold this. So let me write this charge Q is stationary, this one, the left one, stationary. Maybe it wants to move, but we don't let it move, don't let it go, so it's stationary. And then, at initial moment of time, we release this charge. And so, of course, what is this charge going to do? Of course, it is going to be repelled from that one, and of course, it is going to move that way, right? So, let's say, this is stationary, and let's say at a certain moment of time, of course, this charge is going to be at the distance 4 times this distance d. Okay, I don't think that I have enough whiteboard, so it will not be in scale. So let's say at a certain moment of time, this distance is going to be 4 times d. And that's our charge Q. So that's final situation. So this initial velocity v naught is 0. And so now we are interested in the velocity at this moment, when the distance between these two charges is 4d. Right, so that's our velocity. Right, so we need to find that velocity. So let me check what else is given. I think I gave everything. Released, so v equals 0. That is stationary. Yeah. In this case, energy approach is the easiest approach. Again, in the recitation classes, I justified, and maybe here I will justify one more time, why the force approach in this problem, is significantly more complicated. So let me write the approach number 2. It's an energy approach. In this case, it's much easier. So which is based on the conservation of mechanical energy, you remember, right? So it doesn't matter at which moment of time you look at this system, total mechanical energy of this charge, for example, it doesn't matter if it's here, here, or here, you can calculate, and total mechanical energy is going to be exactly the same, right? So if it's true, then we can for example, compare total mechanical energy at this moment of time and this moment of time, and that should allow us to calculate what needs to be found. Okay, so E initial equals to E final. Again, E, it's a total mechanical energy. Classical beginning. And so now we just need to keep diving deeper and deeper and deeper until we will see what is given and what needs to be found at the very bottom, and we should be able to solve what is unknown. So the next step, of course, it's a K initial plus U initial kinetic energy, potential energy at the initial moment of time, equals to K final plus U final. And so what can you say about the kinetic energy at the initial moment of time? Kinetic energy, this object, this charge is released. Maybe I can write it's released. So it means that initial kinetic energy is 0. V naught equals to 0. So it simplifies immediately. And nothing else is 0. So our unknown is over here, right? So now let's write down explicitly. But first, what's the potential energy? Which expression for the potential energy we have to use? It's a system of 2-point charges, and we need to find the right formula, right? So system of 2-point charges, potential energy is KQ, small q capital, over R. In our case, we have two identical charges, so it will be Q capital, right? But anyway, so let me write first in general. So it's a K, Q small, Q capital over R. So again, let me frame it sort of. It is in general, so we need to plug it over there. Right? So this is K Q capital squared. Again, I said charges are the same. And initial distance D then equals to final, it's a 1 over 2 mv squared. And then, of course, kinetic potential energy at the final moment of time, K, again, Q squared divided by 4 times D. Right. And see what? This is basically given charge. Distance is given. This is given. This is our unknown. Again, this is given. One equation, one unknown. Physics is basically over. So now we just need to solve it for V, which is unknown, right? One equation, one unknown. All right, so I will move this term to that side with minus, and then of course I will flip the equation so that my unknown will be on the left-hand side. So it will be mv squared over 2 equals to this minus that. So it will be k q squared over d minus k q squared over 4d. And guys, at this point, I was surprised when I think it's from one of the previous year exams, and I was surprised when I saw how much students struggle with subtraction, this and that term. Lots of mistakes was here at very at the point where you guys shouldn't be making mistakes, because you should be easily able to subtract fractions. So what do we have to do here? We just need to bring to the common denominator. So here we have 4d, here we have d. So we just need to multiply numerator and denominator by 4. Let me use different color. 4 and 4. And now we have common denominator, and of course we can easily subtract these two numbers. I was surprised to see many mistakes at this point. So it will be 4q squared minus q squared, so it will be 3q squared, and of course k is in front. K, 3q squared divided by 4 times d. Right? So, and now m goes in the denominator, 2 goes in the numerator, and that will be the answer basically. V squared equals to, okay, these two can be cancelled. Okay, I will do it later. So it will be k 6q squared over 4m times d. And now, of course, 2 can be cancelled. Right? We can simplify it slightly. So v equals to square root of 3k q squared divided by 2md. You see, I just remove factor of 2 here and factor of 2 there. So we have 3 over 2. Right? And of course, I took a square root. Of course, you can take q squared outside, but at this point, it's not a significant simplification. So that's the answer. Numbers are not given, so pretty much you just leave in the form of this expression. And guys, as I told you, the problem like this, you have to apply, in the problem like this, you have to apply energy approach, because force approach here gives significantly more complicated solution. Why? Because, let me just quickly state that force approach. Look, force approach, of course, is based on the force and Newton's second law. Electric force, Coulomb's law, right? So it will be, of course, ku squared over r squared. And then, of course, we need to combine it with Newton's second law in order to find acceleration. So equals m times a. And if I solve it for a, I'm getting what? Mass goes over there, downstairs, so we'll get kq squared over mr squared. And usually in the force approach, once we find acceleration, we start using kinematic equations. But can we use kinematic equations now? We cannot. Because you see, we have r downstairs. And what happens with r as this charge fly? It increases, it changes all the time. So acceleration is not constant. And I can write immediately kinematic equations cannot be used. In this case, you will have to just solve second order differential equation, which is more complicated, right? So that's why in this problem, it's way easier to use energy approach. So I can write kinematic equations cannot be used. Right. There are some problems where pretty much both approaches are equally easy, equally good, but in this type of problems, energy approach is easier. Okay. Again, if you need some additional explanations, tell me. Right. Okay, that's. You can move it. And you know what? Before I move to the next problem, let me discuss quickly one conceptual question, and then I will solve something similar, but for a charge inside of the capacitor. Actually, what about the time? So 2 hours. Okay. So now let me ask this conceptual question. CQ. It's not related. Problem is solved. Right? Not related to this problem. So what if we have this situation? We have negative charge over here, minus Q capital. Can you see it? You know what? Let me write outside of this sign. So that's my charge and minus Q capital. And there is an electron flying like this. So, and that's an electron. And you see the direction of its motion. So that's basically a trajectory of that electron. Right? And we need to answer the question, what happens with the potential energy? You remember, potential energy, it is an energy of interactions. You need to have at least two objects, right? And that's what we have. We have first charged object, second one. Of course, they interact. Of course, we can talk about potential energy. Of course, we can talk about potential energy. So let me write formula in general. So it's a kq over q over r, right? And so, yeah, we just need to answer the question, what happens to the potential energy with time? And you remember we had in our clicker question in one of our lectures. So what is r? It's a distance between these charged particles, r, right? So first of all, is potential energy positive or negative? Since both charges are negative, so it's a minus q, electron also negatively charged, so it means that potential energy is positive. Both negative charges. Okay, both charges are negative. Right. So potential energy is positive. And then we need to see what happens again in time. Is it growing? Is it going down? All right. Okay, so now we just need to see what happens in time. So r, as electron flies this way, r is getting smaller and smaller and smaller and smaller. Right? So r getting smaller, so potential energy, and since that r is in the denominator, so potential energy, of course, is growing. Right? Denominator is getting smaller. The function is growing, and since it's positive, so potential energy is positive and constantly growing, right? Actually growing till this point, and then we don't know what this electron is going to do, right? How it is going to move. But between, for example, this point and that point, potential energy is going to be positive and growing. So U is positive and increasing and increasing, right? If this charge, for example, was positive, this Q capital was positive, then of course potential energy would be negative, and absolute value would be still increasing, absolute value increasing, but the potential energy is negative, so it means that potential energy would be getting more and more and more negative, right? So it means that it's decreasing. But in this case, since potential energy is positive and increasing, of course it is increasing. Okay, again, a few times I gave in the past questions like this. Actually, this is from one of the exams in the past, so I decided to use that.
So let's say that was so if that was a proton, it would be decreasing then, because it would be
okay,
a positive and a negative charge.
If this was a proton and this charge was still the same, is this the situation?
Yes.
So if this is the proton and that is a negative charge, then of course potential energy would be negative, all the time negative. And then let's see, and then of course look what happens as r, as proton flies, r is getting smaller, absolute value, you see r is getting smaller and smaller and smaller. So it means that absolute value of u would be still growing, absolute value. But the potential energy in that case would be negative. So it means that the potential energy would become more and more negative. But a function which is getting more and more negative, it's decreasing, right? Because out of two negative numbers, which one is larger? The one which is less negative. You see? So
yeah,
if we have if you have a proton, potential energy would become negative. And the absolute value of that potential energy would be growing, again, absolute value. And since it's also negative, so it means that potential energy would become more and more and more negative. Absolute value is growing, so it means that it becomes more and more negative. It's similar, you ask the situation similar to the one which we had in our lecture clicker question. Make sense?
Yes, thank you.
Yeah, it's a very simple analysis, but you just need to make these two steps all the time. First, find out if the potential energy positive and negative, and then what happens to the absolute value of the potential energy. Right. Next, okay, next is, let's discuss basically similar to this situation, but charge will be moving inside of a capacitor, right? Basically, point charge exposed to a uniform electric field, and we solve these problems in our recitation classes, finding some final velocity, position, or travel time, something like that. So, okay, let me refresh what's the situation. Again, so we have a capacitor, parallel plate capacitor, and then there is an electron which is shot from the positive electrode. So there is initial velocity. Okay, let me start drawing the picture. Otherwise, it's difficult to see the whole story. So we have, let me first write an electron inside of a parallel plate capacitor. Right. And so let me draw. So that's the first electrode, then second electrode. Right. This is negatively charged. I arranged it in this way so that it's positively charged. Right. Okay, to make picture look better, let me draw electric field lines. It just makes picture look better. Then an electron is shot from these positive electrodes, so it's a electron, and initial velocity v0, let me write it down, v0 equals to, where's the, here's the number, 1 times 10 to the power of 7 meters per second. Okay, quite a speed. Then the value of the electric field is also given. E equals to 12,000 newtons per coulombs. Or again, volts per meters can be used. Newtons per coulombs, volts per meters, basically it's the same. Then distance between electrodes is also given. D equals to 40 millimeters. Yeah, and then of course universal constants. Of course, I'm not going to write that up. So let's first see what happens to the electron, and then we'll be able to write what needs to be found. So this electron, of course, it is repelled by this negative electrode and of course attracted by the positive electrode. So of course there will be force to the left, decelerating electron. Right, so of course this initial velocity is essential. If we did not have this initial velocity, this electron wouldn't move anywhere, it will just stay there, right? So, but since we have initial velocity, so it will travel for some time, and actually it is going to stop at a certain moment. It will reach turning point, turns around, and it will start moving in the opposite direction. So we just need to find that turning point. We just need to find position of the turning point. Actually, the question actually asks, find the distance of closest approach of the electron to this plate, negative plate. Right. Okay, so since we need to find positions, let me introduce coordinate system. And you know what? I'm thinking, which approach should I use? Probably first I will use energy approach. Let me start with the energy approach. Yeah. And so let me write it over here, and then I will continue. So let's use first energy approach. Which is again based on the conservation of mechanical energy, right? And for the energy approach, so what we have charge in the parallel plate capacitor inside of a uniform electric field, of course, we will have to use the correct formula for the potential energy. This one, U equals QES. And you need to remember that S in this formula is measured from the negative electrode. because that's how we derive this formula, and I did it in the lecture. So S is measured from the negative electrode, and you see that's what I drew over here. So let me also introduce this coordinate system over here. But at this picture, you see negative electrode is over here. So I need to draw my coordinate system like this. So that's my S, and that is 0. Right? You see, in order to match this. So S starts at the negative electrode and goes towards the positive electrode growing, right? And this is D, right? So now, this is our initial point, right? And of course, this is our final point. So it means that over here we have S initial, and that will be our S final. Right, I'm just preparing my picture for the solution, right? So first electron was there, so it's our initial point, and then finally electron will be there. So that's our final point.
Yeah.
Okay, and now let's start. Yeah.
So the S is flipped now because it's going back to the because it's attracted to the positive.
Because I'm shooting electron this way. You know, I could have drawn picture like this, and it wouldn't hurt if I flipped it. Negative electrode would be there, but then electron will be shot in that direction.
Oh, okay.
So pretty much, because I drew negative electrode over there, I just wanted to shoot electron to the right. So I have to position my positive electrode on that side. And since all the time S is measured from the negative electrode, and since my negative electrode on this side, I had to flip S axis.
Yeah. I see why it's flipped now.
Because all the time in this formula, S is measured from the negative electrode. So I need to position my origin at the negative electrode here. So I position origin here and point S axis that way.
All right, yes.
Because I remember, and I keep reminding you guys, remember that S is measured from negative electrode, because that's how we derive that formula.
All right, perfect.
Because otherwise you will start getting some additional minuses or pluses where you're supposed to get minuses, and I've seen it in the past. And of course, students, they realize that something is fishy, that minus shouldn't be there, so they start hiding it somewhere, right? And of course, I can see that immediately, right? All right. So that's why you have to be careful, right? So if S from the negative electrode, draw it. So now this is initial, that is final. So you have to be consistent. Okay, so let me get more water. And so conservation of mechanical energy. E initial equals to E final. Again, beginning, classical beginning. And now we just need to dive deeper and deeper and deeper, revealing all the truth about total mechanical energy at each moment. So K initial plus U initial equals to K final plus U final. And usually at this point I start thinking, what can be dumped if there are any zeros, right? Initial point, potential energy is not zero, kinetic energy is not zero, but what final point, kinetic energy is 0, because that's the turning point, right? So at this point, I can show that V equals to 0, because that's the turning point. Electron stops for a moment, turns around, and start moving in the opposite direction. So for a moment, velocity is 0. So it means that in this equation, K final is 0, because V equals to 0. Okay, maybe I can add subscript F. Right. Okay, at least some simplification. Then, again, which formula must be used? In the previous, which we erased, we used this potential energy of 2-point charges. Now we don't have 2-point charges. We have a charge exposed to the uniform electric field, which is created by the capacitor, so we need to use that. It's another place where some students just use the wrong formulas, right? So let me write potential energy equals to K. Wait, I said it's wrong and started writing with K. Sorry, you didn't see that. QES, QES. So that's what we need to use instead of our U's, potential energies, right? Okay, so now let me start explicitly writing K 1 over 2m v naught squared, so this, then plus Q E, and this is initial point, so S initial. And what's the value of S initial? Okay, let me do it one step at a time. So S initial. And what's the value of S initial? The electron is shot from the
zero.
No, carefully. Look, that's why you need to look at the coordinate system.
Oh, shoot, yeah.
That's where students usually start losing their minuses or getting additional minuses, because you just need to look at the picture and must be consistent with what you see. Of course, yeah, as I said, you can draw it in a different way, but still you have to keep track what is initial, what is final, otherwise you will start losing minuses or getting minuses, unnecessary minuses. So S initial in this case is D, because the electron is shot from the positive electrode. Position of the positive electrode is D. 0 is at the negative electrode.
Yeah.
Make sense? You see that?
Yeah, makes sense.
Yeah. So let me use even red. So that is D, and even show that that's where and that's why I keep encouraging students, guys, draw a nice picture, even graduate students, draw a nice picture, because it will help you, right? It reduces chances of making mistakes. So now this is 0, and it must be equal to the final potential energy. Again, Q, the value of the electric field, and now S final. And the value of S final, it's basically that's what we need to find. S final, that's our effectively question. We just need to find the point where the electron turns around, turning point. Actually, the question asks about how close the electron is going to reach the negative electrode, but basically it's this distance, right? So it will be D minus S final. Once you find S final, D minus S final, so it will be this distance, which is, that's what problem wants to see, wants to know. So, but for now, effectively, I can say that this is our unknown. Right? And given unknown. One equation, one unknown. What can be easier than that, right? At this point, we can say physics is over. Now we just need to solve it for S final. So, of course, I need to flip the equation. So to have my unknown to the left-hand side, and then I have to multiply, of course, the whole equation. Okay, divided by QE in order to remove any constant factors in front of my unknown. So it's basically dividing this by QE, dividing this by QE, right? And of course, flipping. So as far as F will be on the left-hand side. So then this S initial, right? And then plus mv naught squared divided by 2QE, right? And S initial is our D. Plus mv naught squared divided by 2. Quick question. This term, is it going to be positive or negative? Because it looks like we're getting what? We're trying to find this S final, which is supposed to be less than S initial, because again,
So,
S is increasing this way.
So it would be negative?
Yes, it must be negative, because charge is negative. Because something must be subtracted from S initial to get the smaller value of S.
Yeah.
Right? But since charge is negative, and that's why I started rewriting. Okay, let me write it like this: absolute value of the charge, and then I will remove that plus and put minus. So that minus is connected to that charge. Right? Electron, since we're dealing with the electron. So there must be subtraction. Right? And so now the rest, just you need to plug numbers, calculate, and of course I'm not going to do it, and I will just write down the answer. So it will be okay, I will write it. Okay, let me write first in meters and then in centimeters. So it's a 0.023. Okay, maybe some additional sig fig. And then the closest distance, and then the closest distance to distance to the negative electrode, So effectively, the problem asks about this distance, right? So that's effectively we need to find, right? So we found SF. Yeah, we already found it. So it's already what we needed to find. Okay, since I position my coordinate system, so SF, it's this distance, and that's what problem wants to see. Okay, so that's the answer. Hold it. Yeah. I was just looking sometimes at the force approach, sometimes energy approach, and sometimes got confused. No, that's the correct answer. So that's what we wanted to know, and that's what SF is, right? The closest distance to the negative electrode. So that's the solution to this problem, right? Using energy approach. And so now let's solve using the force approach. But for this problem, they are both equally easy. So that was the second, and now first force approach. And in my picture, I changed my coordinate system for the force approach. Although I don't know why, but since I'm going to send this node, so let me follow my nodes. Right. And again, it's not a crime. You can basically it's sort of like your constitutional freedom to choose any coordinate system you want for any problem, except for, of course, if you derived a formula and S, like in this case, is measured from the negative electrode, then you're basically stuck with the coordinate system, which is supposed to start at the negative electrode. Right? Otherwise, you will start getting some strange results. But if the formulas are not connected that well to your coordinate system, then you can play with that any way you want. Okay, so now let me draw additional picture. So that will be one electrode, then this is the second electrode, this is still negative. This will be my positive. Right. And now let me orient my coordinate system this way. S, this is 0. Because again, now I'm not going to use this formula. So I'm not now restricted in terms of the fact that S is measured from the negative electrode. Now, in the force approach, it's up to me completely. So now I decided to position my origin at the positive electrode. So now, of course, I can draw electric field, right? And again, the same trajectory will be. So first it will travel this way, then it stops, and it will move in the opposite direction. So this will be my S initial still. This will be my S final. Right. And so the force approach, which is based on Newton's second law and the expression for the electric force. So first Newton's second law, F equals ma, and of course this force is an electric force. Okay, so let me write electric force. Since we have expression for the electric field, not expression, the number, the value is given, right? So I can write electric force equals to Q times E. And again, since Q is negative, it's an electron, so the electric force is going to point that way. So my acceleration is going to be negative, right? Okay, so now let me plug it. And of course, from here, I can get acceleration equals to F divided by M. So it will be equal to QE divided by M. And again, since this is negative, again, it's negative. So the electron is going to experience acceleration this way, decelerating. So acceleration is going to be negative, right? And so now we found acceleration QE divided by M, and since acceleration is constant, so kinematic equations can be used. But again, you remember when we had that problem, the previous one, when we had 2-point charges flying away from each other. In that problem, kinematic equations couldn't be used because acceleration was not constant. But here acceleration is constant, Q constant, E constant, mass is constant, acceleration is constant. Right? So it can be used. And so which kinematic equation is the best one? Usually, if the question is not about finding the travel time, and it's not, and we don't have any information about time, so it means that most likely the most convenient formula will be the last one, no time equation, right? So the most convenient will be this one, v squared equals to v naught squared plus 2a, and then usually delta x, but in this case it's not x, we have s, so it will be s final minus s initial, delta s. But again, in the kinematic equations, we had just delta x. But instead of x, we use s's. Okay, so now, simplifications. Final velocity, this final velocity, of course, is 0 again. V equals 0, it's here, right? V final. So we can dump it. And so initial velocity is given. Acceleration we just found, right? Final position, where is our final position? That's what we need basically to find. That's our question, right? And initial position is 0 because now I orient my coordinate system in such a way so that now initial position is 0. So that is 0. So solve it for SF. So it will be, again, let me do it one step at a time. 2ASF equals to V naught goes to that side with minus. So it will be minus V sub 0 squared. And so SF equals to minus V naught to the power of 2 divided by 2A. And acceleration we already found. And again, acceleration will be negative because charge is negative. So now let me plug expression for the acceleration, minus V naught squared divided by 2 times this. Q E divided by M. And again, charge is negative. Let me emphasize, charge is negative. Again, let me show that minus explicitly. So minus from there, minus from here will give us plus. So SF will be positive as it's supposed to be, right? So it will be V naught squared divided by 2 absolute value of the charge, E, and mass, of course, goes upstairs. This M will go in the denominator. Oh, numerator, sorry, numerator. And again, this minus disappeared because of the minus of the electron, charge of the electron. So the result, we have plus. Okay, but now look, what are we getting? SF, now it says this distance, right? SF. But the question is about finding this, right? So over here, you see, I showed it, and also here. So now in order to find that distance, we need to do what? We need to take D, which is the distance between the electrodes. This is D. So D minus SF, and that will be the distance. Okay, let me label it as X, this distance as X. Right. So, okay, let me move to this side. So finally, X will be equal to D minus SF, right? So that will be the that distance which problem wants to find. Okay, I can write so this same as over here. So in the last stretch about connections between the electric field and the electric potential, and we'll call it a day at this point. So E and D, you know what, let me write which exactly bridge I'm going to use. So we need to find information about the electric potential from the information about the electric field. So we need to use this bridge. From E, we need to find V. And again, it's very similar to what we discussed in our recitation classes. So we have a plot. E sub x versus x. E sub x in terms of volts per meters, and versus x in meters. Then some numbers, okay, probably first draw the graph and then, so that's the graph. And now numbers. Let's say this is 200. Okay, this is 100. Then this is negative 100. And then 1, 2, and 3. 1, 2, and 3. So this plot is given, and also we know that electric potential at x equals 0, basically over here, electric potential at this point is what? Minus 50 volts. Okay, minus 50 volts. So we need to find the value of the electric potential at x equals to 3 meters. Basically at this point, we just need to find the electric potential at this point. So we have a bridge which allows us to move between the electric field and the electric potential. So let's just apply it. Right. So delta V equals to, okay, let me write explicitly V final minus V initial equals to minus integral from x initial to x final Ex dx. So I just rewrote this. Right. Okay, and first step that we have to apply all the time before we can start using this formula, we need to make a decision about the initial and the final point. So initial point. Since we have some information about the electric potential at the origin, so let's take that point as our initial point. So let x equals 0 be our initial point. And since we want to find the electric potential at that point, so that will be our final point. So let x equals to, okay, not d, 3. X equals to 3 be our final point. Okay, so now after this we can write this formula for our particular situation. So V final, so it's a V at 3, final point, minus V at 0 at the origin, right? And equals to minus integral from 0 to 3 ex dx. Function is reasonably simple. You can integrate if you want, but again, as we discussed, we're going to use the graphical interpretation of the integral. So it's basically this integral equals to the area under the curve E versus X. So we just need to find this area and that area, add them, and put the minus in front. So that will be the value, the right-hand side. And of course, then of course, we will have to include this V sub 0. So now let me take care of that integral. So it will be equal to minus, and I will write area of two figures, this triangle and that triangle. So let me label them. This point O, for example, this point A, this point B, point C, and point D. So let me write area of a triangle OAB, and then plus area of a triangle BCD. Triangle BCD, right? Okay. Now just simple areas. Minus area of a triangle, it's 1 over 2 height times the base. So it will be 1 over 2. Height is negative, minus 100. So minus 100 volts per meters. And times the base is 1 times 1 meter. So that's the triangle of this area of this small triangle. And then area of this big triangle. So plus 1 over 2. Height is 200 times 200 volts per meters. And the base is 3 minus 1. Base is 3 minus 1. 3 minus 1 meters. Okay, I need this space. So let's calculate this. Right-hand side, minus 50. Then 400, so it looks like this will be 200. Minus 50, it looks like we're going to get plus 150 and minus in front, so it's a minus 150. Yeah, so it's a minus 150 volts. So that's the value of this integral with minus. But we need to find this. We need to find this. So let's just solve it for that. So V sub 3 equals, this goes to that side with plus, V sub 0 and minus 150 volts. Right. So that term went there. So V sub 0 is given minus 50 volts. So minus 50 volts and minus 150 volts. So overall, we're getting that the value of the potential at point 3 equals to minus 200 volts. So potential is going down. So first at the origin, potential is negative minus 50. And then as you move to the right, potential is getting smaller and smaller and smaller. So at point 3 is minus 200 volts. So you see, it's not
So
complicated. Yeah.
You subtract the 150 because it's negative, right? Like if that was a... Okay, yeah, that makes sense.
Okay. So again, it's a very common place for mistakes because you have to move to the other side, negative value, right? So minuses from the formulas and so on. So first, I calculated this right-hand side with this minus. And this right-hand side, let me even frame, okay, this equals to minus 150, right? And so now I just need to move this term to that side with plus, and that's what I got here. Plus V naught And the value of that integral is minus 150. See it?
Yes, that makes sense. Thank you.
And of course, the value of V naught actually is negative. So it will be minus 50 and minus 150. So we have two negative numbers. We just need to add them to the negative 200. Yeah, it's a yeah, I want to say simple, but of course you need to practice it. All right, and of course be careful in terms of moving terms around, right? Because again, as I said, not often, but some students make these mistakes, unnecessary mistakes, when they move negative term to the other side, and they start losing minuses or adding minuses, right? As a result gets somewhat messed up. Great. So now the last one, and the last one is very simple. It's even simpler than that, because now we need to practice the bridge in the opposite direction. So how to get from the electric field. So pretty much now you just need to look at the slope of the curve, if the curve is given, and add minus in front, negative slope. Right? Boy, this picture is more complicated to draw. Again, probably first I will draw the picture and then I will put numbers. Okay, so not straight, but okay, straight enough. Volts, electric potential, units of volts. Then x-axis, okay, R, but let me change to X. It's not a big deal. So X in meters. And so we have this plot. Let me first label this 1, 2. I need 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 meters. Then 4 and minus 4. So let's say this is 2, this is 4. 4 volts, and here we'll have minus 2 and minus 4. Right. So now plot. First function is going up to this point. Okay, red. To this point. Straight line. At least my intention, to draw a straight line. Then within 1 meter, this function drops to negative 4. It's a serious drop, and the line is too big, so let me use the ruler. And then it stays constant up to 0.6. Right, so this is the curve. And so we need to plot, no, we just need to find the values of the electric field in this problem. So let me write, so we need to find electric field. Of course, x component of the electric field, because everything happens along x-axis. We cannot say anything about the y and z-axis, right? So we assume it's 0. So we need to move basically from V, because that's what we have, and we need to go to the electric field. And of course, that's the bridge. So let me write that formula. So Ex equals to minus dV over dx. And before I start calculating, right, obviously we'll have to divide this problem into 3 parts, because we just need to find slope, and we have a certain value of the slope in this part of the curve, then in this part of the curve, and that part. So we need to divide this problem into 3 parts. So part number 1 here, second part here, and the third part will be there, right? And before I start calculating actually slopes, I need to change this formula slightly. Let me write underneath. So Ex equals to minus dv over dx, and since we have straight lines only, so we can change this formula to from dv over dx to minus delta v over delta x. Why? Because again, this is slope, and for a straight line it doesn't matter if you use infinitesimally small increment dx to calculate the slope, infinitesimally small increment over, or if you use finite increment, for example, between 0.0 and 3. So slope will be the same because we have straight lines. Slope is exactly the same at all points, of course, of these three regions. All right. So we can use that, and we will use it several times in this course, this trick. And again, I can write that it's only true for straight lines. So we can replace dv over dx with delta v over delta x. And now three regions. Region number 1. So E sub 1 in the first region. So minus, so v final, okay, delta v, of course, it's a v final, and the final point is at 3, v3 minus v0. So I just wrote delta v, final point, initial point in the first region, and divided by delta x, which is 3 minus 0. 3 minus 0, and of course that is in meters. Okay, so now let's plug numbers. 4 volts minus 0, and divided by 3 meters. So it will be minus 4/3 volts per meter. Minus 4 over 3 volts per meters. As I told, these problems are even easier than the previous one. So now region number 2. Region number 2, E sub 2. Again, it will be minus dv over delta v over delta x. And now, again, minus. And final value of v, final, it's this point, which is minus 4 volts. So minus 4 volts. Then minus because it's delta, right? Final value of potential minus initial value of potential. And initial value of the potential, the value of the potential at the initial point, 4 volts. So minus 4 minus 4. And divided by the change in the x, so 4 minus 3 meters. So 4 minus 3 meters. Right. Okay, so what are we getting? This is 1, this is 8, minus 8. Minus 8 minus another minus, so it's a plus. So we're getting, what, 8 volts per meters? Let me check. Yeah, it's actually correct. 8 volts per meters. And again, what does it mean, positive electric field? It means on this part of the curve, electric field points this way. And again, what does it mean, this negative electric field? It means on this part of the curve, electric field points that way. So negative, it means that points in the negative x direction. And region number 3, there is nothing to discuss about region number 3. Electric potential stays constant, so of course slope is 0, so the electric field is 0. So delta v is 0, so electric field will be 0. So E on the third region, of course, will be 0, since v is constant. So that's it. That's what I was planning to discuss. Again, as I told at the very beginning, I was not planning to discuss complicated problems, so something new. No, all the problems of the level similar to the problems which we discussed in our recitation classes and which you had in your homeworks. Right? And again, that's my policy. Exam problems must be very, very similar. Okay, at least on the same level.